channel. This time I'm going to be talking about focusing in Kstars Ekos using the HFR adjusted focus measure. So I'm going to start off with a little bit of theory and then we'll move into Ekos and just show you a quick demo. So over here on the right of my screen, I've got a couple of graphs that I've drawn. The top one is just a standard normal or Gaussian distribution in 2 dimensions. You've got the intensity on the vertical axis and distance, let's say in pixels, along the x-axis. Now the interesting thing to note about normal distributions is that the width of them, so you know the HFR, is independent of the intensity, and yet you know we all know that when we look at pictures of deep space, we all know that stars are wider when they're brighter and the fainter ones are always smaller. So you know, over here on my Fitz viewer in Ekos, it's very clear this star here, which I've got my cursor on, is brighter. It's not saturated, and it's got a bigger HFR than some of these fainter stars. So we're all well aware of that, and yet the theory says otherwise. So you know, what gives? Well, there's a couple of things in play. The first is that you know not all stars are equal. Some are in different stages of their life cycle, burning brighter, burning less bright, etc. Some are bigger, some are smaller. So there are sort of those sort of factors. But one other factor I think that I became slightly interested in is the fact that it isn't just the normal distribution that's relevant. It's the fact that the HFR calculation background subtracts the intensities before working out the HFR, and the reason it does that is that obviously as the star intensity trails off, the star in effect disappears into the background. So for a normal distribution, this tail of the star never quite reaches zero. It's always fractionally above zero. But in real life, of course, when we try and measure that, we have to put some sort of limit on it, and the limit is, of course, the background intensity. So what I've done in this lower graph is I've assumed a background, in this case of 0.01, and I've just background subtracted the intensities in the top graph to give the bottom graph. Now, obviously, what you can see is that the intensity does actually drop to zero in this case, and you don't have this sort of this much wider tail to the star. Now, what that actually means is that the intensity has dropped a little bit, but it also means that the measured width of the star, be it the HFR or full width half max, is actually a bit smaller in this case than in the top case. So what we're actually seeing where we measure the stars by background subtracting them is we actually see a slightly smaller HFR value than would be the case if we weren't to background subtract. So that got me thinking, and one of the things I decided to do was take a focus frame and plot the measured HFR, which is on the y-axis here, against the star magnitude. Now obviously there's some variation, there's some randomness in here. Obviously some of these stars are perhaps in different stages of their life cycle, etc. But you notice that there is an overall trend, and the trend is that the HFR is bigger for brighter stars over on the left, and for dimmer stars the HFR is smaller. And interestingly, you can put a straight line through it. Now you can argue that maybe a curve would be better, but it's it's, you know, a straight line isn't bad for this data set. So it obviously doesn't explain all of the variation, but there is clearly a trend here, which relates the HFR to the magnitude of the star. Okay, so what does that all mean then? So the next thing I did was a bit of maths, and came up with this formula at the top. So I'm not going to go through that in much detail, other than to say what the theory would give you is that what I have here, the HFR on the left of the equation, is, if you like, the real HFR, and that is a product of two things. One is the measured HFR, which is the background subtracted HFR that Ekos measures, and there's this factor. So don't worry too much about what this factor is, but it is related to what I've called B over A. So B is the background intensity and A is the peak intensity of the star. So if you imagine for very bright stars where the background is negligible, this fraction B over A tends to 0. So what this multiplicative factor tends to is the error function of infinity, which is 1 over 1 minus 0, or approximately 0, which is 1. So this factor tends to 1 for the case of very bright stars. So I plotted down here on the y-axis the factor, this term here, and on the x-axis I've plotted B over A. So in the case where we have a very bright star, where the background is is negligible in comparison to the peak intensity of the star, the B over A factor is very small, so it's tending to 0, and the multiplicative factor tends to 1 in that case. As the star gets, or the stars get dimmer, so the B over A factor starts to increase, and this is where you can see this line starting to increase. So what that's telling us is that for fainter stars, the value of this term is getting bigger. So right over here on the right hand side of the graph, there's a multiplicative factor of 1.3. So what this is saying is what we sort of observe, which is as stars get fainter and fainter, so the measured value of the HFR gets smaller, and therefore to return it to the true HFR, we need to multiply the measured value by a bigger and bigger number. So this relationship gives you almost a straight line. I mean, it's not quite a straight line because this is more complicated mathematical function, but over the range of values I plotted here, it is actually relatively straight, which sort of fits with the earlier observations I had of my own data, where I'd plotted star magnitude against HFR and had seen that sort of somewhat linear relationship. So this is now built into Ekos, and I've done another graph here where the blue data set is the data set I showed you earlier, which has got this tendency to show a smaller HFR as the magnitude of the star increases or its intensity decreases, and then the orange data set is where I've used the calculation I just showed you to correct the value of the HFR. So you can see it does a reasonable job of turning this blue sloping line into a a much more level sort of relationship, which is, indicating that it's, somewhat on the right lines. So the idea, obviously, within this is that where we measure, lots of stars in a focus frame, we're trying to compare those stars and get an average value of some sort. Now, clearly, the stats work a lot better if you're comparing, apples with apples. If you're comparing apples with bananas, of course, the stats are not really so useful. So I think the advantage of the HFR adjusted method is that it tries to make the stars, a little bit more similar, so that the comparison that the focus process uses becomes a little bit more relevant. Now, clearly, there's still a lot of noise in these measurements, and therefore this little mathematical trick doesn't, compensate for everything. But I think it does nudge things in the right direction. So that's the theory. So let's kind of see how it works. So back to Ekos. I've loaded up HFR, an HFR focus run, again on sort of my data, usual sort of set of parameters, etc. And it's come up with a nice curve, and a nice solution. So what I'll do is I'll just copy this off so we've got it for reference. Just keep this over here. Okay. So what I'll do now is I'll do the same thing, except I will choose HFR Adj as the focus measure. So this is all you need to do to run it. It's not necessary to change anything else, only the measure from HFR to the HFR adjusted, and then just let it run. Now, so there's a few things that I would normally expect if you're using the HFR Adj versus the regular HFR. The first thing is that because we are multiplying each of the HFR values by a number that is always going to be slightly bigger than 1, I would expect the HFR values to the HFR Adj values to always be bigger than the equivalent HFR values. That's just the nature of the mathematical relationship. So, the fact that the HFR numbers here are bigger, so in this case, the focus point HFR is 1.73 versus the focus point of the plain HFR is 1.5. That doesn't mean that something's gone wrong or whatever. It's just a fact that the numbers are different. So that's point 1. Point 2, because we are comparing stars now that have an adjusted HFR, and the whole purpose of adjusting it is to make them more similar, I would expect that the error bars on the measures will be smaller. And this is true. So it's more notable on the points with bigger error bars. So let's just look at 0.9 here. The size of the error bars are a little bit bigger. So it's doing its job in the sense of what the HFR is trying to do is to make the stars more comparable with one another. And obviously a measure of that is the size of the error bars on this graph. So the fact that they are smaller, is indicative of it kind of doing its job. Other than that, you have a very similar curve. The R-squared values are the same, and the focus point is 1 tick out. So in essence, it's the same. I think on my rig which is very tolerant for focus purposes, you know, there is a small but noticeable benefit to using the HFR adjusted calculation versus the standard HFR, but I don't think it is significant enough to make any difference to the focus point. For folks with perhaps more sensitive rigs, you might want to give this a go, because you know, it might turn out to give you a slightly better focus. So as I say, this is not, you know, going to, you know, revolutionize HFR you know, at all, but I think it does kind of nudge things a little bit towards getting a slightly better calculation. So you know, why not give it a go? It's all you have to do is change one combo box, and that's it. You can use it. So clear skies, and I'll see you next time.